'Cause if I say it on stream, then it has to be true, right? That's the trick. Questions where you want deadlines to be moved and things like that, it's best to punk me when the camera's going, like right now. Because then when I'm like, I don't remember saying that, you can link it to me. If I say it off stream, I can just forget. So today is that right? We'll pretend it is. Today is March 2025 here at ASU. And we are hopefully going to start talking about Windows and how Windows kind of differs from the, yes, I know. It's the same mistake I made last time. How Windows differs a bit from what we've seen in Linux. Now, this module is super, I'm going to say, bare bones, and that's because a lot of the pain is in the implementation and just making sure that things are working as you expect. There is a kind of follow-up Windows module, which is all new content that we'll be dealing with at the other side of spring break. And so this is just hey, let's make sure things behave how we expect, learn a little bit about what's different. Should be a pretty chill assignment. So, memes. We didn't get a lot of memes, but that's okay, right? The Chosen Talk, classic. A little bit of a meme on the House of Spirit. I don't believe we have House of Spirit in the T2.
I could use it for two of the channels.
Could you?
Well, I do, but I've read someone else did.
Okay. Wait, is that my favorite troll? I don't. It's been so long. I don't remember if that is my favorite troll or not. The handle was familiar. You picked the wrong day. I know. All right. 2 weeks from now is when you really want to hit. Today is going to be quite the yellow. And part of the reason for that is, as I mentioned, I think last week, 365 is doing intercepting communication. They're kind of doing a lot of fork bomb brute force things, and that has not been the greatest on the dojo. I have been told that that's going to be addressed, which is kind of awesome. So hopefully in the near future here, if there are things where they need to brute force or do some type of insane infinite loop, it will not be as impactful. Because it definitely impacted me as I was trying to make some last minute changes on this Windows stuff to make it work. I'm over here trying to fix the Windows stuff, and it's like a 5-second delay when I hit a key, unless it's like 2 a.m, right? Which is why I pushed the final change earlier today. So we're going to have this intro to Windows stuff. This, I think, originally said the 14th. I moved it to the 18th. Just because it doesn't matter, right? There isn't class again until then, so it's kind of a whatever. Honestly, this module, assuming the infra behaves correctly, the module can probably be solved in a day. I'd be surprised if people spend more than 2 on it, unless the infrastructure itself just has problems. The fun stuff will happen when we come back on the other side of spring break. That is where the reason that we made infrastructure changes will start to make sense. Demo plans. So I said I pushed some changes to Windows. I don't know if they've made it to prod yet or not. We'll find out. If not, then we're just gonna wing it. All right, and we'll see if Windows works. So let's go here to pwn.college. I don't believe. Oh yeah, I didn't make it in the classroom. I changed the underlying, yeah, like when you shook your head. So there's still a chance of hope here. So the assignment that will be listed under the class is this. Good night, troll. Will be this Windows crash course. These same 8 challenges. They'll show up right after class. I'll push this before I leave. So there's seven challenges, and they are all pretty easy. The first one is a lie. All right. It says smoke test, start Windows VM connect port 4001. So in prior iterations, as the challenges say up here, right here, getting started. These instructions are a lie. This is what changed. And I'm going to rewrite, I'm going to push changes to that right after class. But what you used to have to do to work with Windows on the Dojo is you had to be in the Linux environment and connect to a very specific port, in this case 4001. That then went to a proxy service that was running on Windows that would then communicate to a service. It had all sorts of like weird IO bugs, and it was pain. And so this semester, see, changes. This semester, we hopefully have something that is a bit more smooth. Start a challenge. Well, SSH hacker at pwn.college. This is still going to drop me into the Windows environment. Oh, it looks like my change did work. So on the Windows challenges, by default, this is going to auto start a virtual machine for you. So my change didn't get pushed, which is nice. If I want to connect to this Windows VM, we can type Windows Connect. It's going to work very similar to like the VM command that we have on the Dojo, except now you're dropping into a Windows VM, and so we have our PowerShell prompt, which is nice. But one of the kind of things that is definitely different about Windows is that Windows has a lot more graphical workflow, right? I really like working in the terminal. There's a lot of things that you can't do on Windows in the terminal as well as you can a GUI, right? And so we probably need to expose some type of desktop like this. Well, if the changes worked, we have desktop Windows. There we go, right? So we launched the challenge. I don't think we'll add a link up here because it's kind of a special case, right? But you can know this path. Desktop-Windows, it'll drop you into the VNC for this right here. Now, there's a couple gotchas here. Like right now, I'm at this lock screen, right? I can't type anything. It says press Control Delete unlock. Does anyone use the VM or the desktop interface board have an idea of what to do here?
I know what to do. I use you go to the left. There's a Control Delete button made already.
Okay, yeah, we go over here to this left-hand side. We mash this key thing. There is a magic button for Control Alt Delete. That gets us through the door here so we can sign in. Now, I launched this. This is just my horrible code. Someday I will put in the time to fix that, but realize it's like a 5-hour loop for me to see if it worked. So you can all hit cancel there. And now we have our Windows interface here. Unfortunately, I haven't figured out how to get the scaling work correctly, so you probably want local scaling, so this way we can see everything on the screen. Now, on a Linux system, we have /flag, we have /challenge. You can't really do that on Windows, just as far as working with this, right? So instead, we have multiple drives, right? Just as an implementation detail. The flag is located at C flag, right? Now I opened this or launched this challenge in practice mode, which means that I do have admin permissions within the Windows environment. And this is important when we get to debugging, which is what we'll kind of run through a little bit here. But as an admin, I can open the flag and I can just see it, right? Windows is a little bit interesting in the sense that their security model, their user model is very different than what we see over on the Linux side, right? On Linux, kind of the reason that we have this challenge binary that we need to exploit is because it is set UID, right? There is actually the equivalent of sudo now on Windows. Microsoft released that like a year ago. But the concept of a set UID bit doesn't exist in Windows. So we have to set up kind of a different barrier here for how we deal with the challenge.
So we just elevate the privilege.
I'm sorry?
So we just elevate the privileges.
So with Windows, if you want to run something to do the equivalent of sudo on Windows, and you've probably done this like hundreds of times without really thinking about what's going on, you right click and you run as administrator, right? Like that is the, I just sudoed on Windows, right? But there is an actual sudo binary that Microsoft released like a year ago for the terminal, where you can actually call like sudo command, and it behaves as one would expect on the Linux side. But what Windows doesn't have is setuid bit, right? That's where the binary runs as somebody else just by default, right? It's chilling on the system. Like if I'm, this won't mean a whole lot in this context, but we have a file here where the Linux permissions for the owner is read write s, where the s is the setuid bit, which means that if I, as the hacker user, were to run this particular file, I can't because it's a Windows executable in Linux, but it would run as if it were the root owner, right? It wouldn't run as the hacker user. And that is how we get that privilege escalation on the Dojo and all of the Linux stuff. Okay? But I can't do the same thing over here in Windows. That was the reason that the old Windows stuff said, hey, connect to this port and do this crazy stuff, because we were doing the privilege escalation in this proxy service that would then launch things as an elevated user. We're doing something similar now. It's just a bit more hidden. So I'm going to hop back and forth and use the terminal when I can. If I do the equivalent of PS on Windows here, I can see all the processes that are running. It's get process in PowerShell. One of the things that is running here is this thing called flag service. All right, flag service is running on all of the Windows VMs. Flag service, as the name kind of implies, has the ability to access the flag, right? If you are not running in practice mode. Yeah, right. If I were to start this up, in normal mode, I have to somehow get the flag service to get the flag. Okay. And the way that the challenge binaries work, I said that there's many drives, right? So C is what you would typically expect on a Windows system, right? This will not persist when you restart the VM. This is just whatever is in the VM. The drives that you're going to be interested in here are X, Y, and Z, or actually Y and Z. Y is where our challenge lives, right? So this is how we are mounting the challenge from the Linux environment into the Windows environment. So we now have a challenge layer. Okay. This PDE file, I'll talk about in a few. The other drive that you'd be interested in is Z. Z is your home directory. So if you are working on a file and want to persist it, right, across challenge starts, please put it in Z. So otherwise, if you restart or start the VM, you're going to lose your work. There is a bit of a gotcha with sometimes if you have something on the Z drive and you try and run it, you'll get a weird error. The way to work, it's because of the way that we're mounting this into Windows. If you get this weird error, the answer is to copy whatever it is. I don't know. Into the C drive. And then run it from here, and then you won't get any complaints. Now, the challenges themselves, wrong drive, are chilling here The first one is aptly named Baby When Smoke Test. This is the moment I get to find out if the infrastructure behaves or does not. This is literally just, does this all get the flag? And the answer is no. All right. So right now, we all get to know that this is broken, which is amazing. This particular message is because the flag service verifies that you are interacting with it from the challenge bindings. I can fix this right now. And this is what I'll have to fix. So you can see this work. This is going to be some magic here. So Windows is interesting from a dev standpoint. In Linux, we can just call GCC, right? Life is great. If we want to build something that's 32-bit or 64-bit or whatever, we configure that by passing arguments to GCC. Right? The Windows dev environment, as I kind of already hinted at, is really meant to be GUI based, right? And so if I just start up a fresh PowerShell terminal here, their compiler is CL. CL doesn't exist over here. In this terminal, I ran this mysterious PowerShell command, right? This PowerShell script that I've written. Now if I type CL, CL exists. Part of configuring the kind of dev environment on Windows is setting a bunch of environment variables, setting up your path, because it isn't just compiler flags that determine these things. CL does take a whole bunch of fancy arguments like you would think, but there's additional configuration in environment variables and path. And so I have this magic dev enter thing to make that work. Okay. Because otherwise, these commands that I type just won't exist if you were to try and do the same thing here. And that's why. So like when you use Visual Studio Code and you say, hey, I'm going to build something, and you do all this configuration, hey, I'm building a C++ program for Windows 10 that's 64-bit. Part of what the Visual Studio program is doing is making sure that before it calls the compiler, it sets all of these environment variables and manually sets all of these paths when calling the compiler to make sure that you're building for the correct target. And that all happens invisibly under the hood. And so my little thing there is a cheat so I can use the terminal like a good boy. It also allows me to use this, which I need. This 256 on why are you not happy? Okay. Good old drive stuff. Look, now it works. So I'll show the code of the flag service because it's on the VM here. But this is what I was expecting to see happen, right? The way that this flag service works, and this is because there's been a large number of unintended behaviors, right, that can happen with this Windows info, is the challenge binaries are signed. And then the flag service is verifying, it's a self-signed cert, verifying that the signature on the binary matches our self-signed cert of pwn.college. And that is the only binary that it will allow for you to get the flag. So you have to exploit whatever's binary it is that's located in the Y directory that we're exposing. Okay. If I go to C, program files, common files, flag service, this is just where we happen to hide this amazing flag service program. And what we see here is there is a send flag program. This happens to be written in C++, but hopefully you can follow along. It's doing exactly what you would think. It's going to open the flag. It's going to write it out, but it's writing it out over a pipe. Windows has these same IPC mechanisms that you are familiar with on Linux, right? We have standard in, we have standard out, we have pipes, we have shared memory. Like all of these same concepts exist. The flag service here is going to write over a pipe. I just want to explain how this thing works. So that way, when things blow up, you have some idea why. Find right here. So once this service starts up with Windows, it's going to wait for someone to connect to this named pipe, right? So we just have this named pipe that exists. And this named pipe is going to start with a bajillion slashes. Maybe. There it is. Because this isn't named pipes on Linux exist on the file system, right? We use like make FIFO, and then we have this pipe that's chilling on the file system. This is not on the file system. We'll take a look at this, why this kind of weirdness happens when we come back from spring break. But everything is like a resource, and like the file system is an abstraction. And so we're accessing a named pipe on the local system just via this path that is in a file system. All right. And so the challenge code is going to open up that same path. It's then going to do something that we can do in Linux, and we do in like the program interaction challenges, where we're going to inspect what is connected on the other side. In this verify client process, we're going to look at what process is on the other side, which is in this. Maybe. This is going to grab the process that is connecting to the flag service and then verify the path to make sure that it is, in fact, a challenge binary. And then it's going to verify that there's a code, that binary has been code signed by pwn.college. Just so you understand like how this mechanism works for how you get the flag. Assuming you pass that check, it will throw out the flag. And this was a little bit of crazy hand wavy stuff on intro. It's probably not super interesting, but it's important that you understand how the challenge is actually getting the flag, right? It isn't calling open flag. Yes.
This is my understanding of what I just saw.
Okay.
So the flag service exe binary checks that the checksum are the binary we have at the Y drive matches what the server in it checks that the SHA is the same.
It's not the SHA. It's not a hash. It is actually public-private key crypto.
Okay.
All right. So.
Well, the hash of the crypto, or the hash of what was it crypto? Or I want
It's
whatever it's checking for something.
It's yeah.
Okay, and then so the what was the name of this program again? The service flag.
Flag service.
Flag service is the one sending the flag to the exe.
Correct.
So what's the exe doing?
So what is the exe doing? Is the question. That's fair. As you know, I have an unhealthy obsession with GDB. Unfortunately, I can't bring my love of GDB over here to Windows. I believe there is GDB on Windows, but I think I'd be doing you a disservice if that is what I actually demoed and used, because I certainly don't think it is the common tool that you see. There are other debuggers, and I'm sure Windows people will be more opinionated on this than me. I'm not a hardcore Windows. There are two debuggers that I will suggest you take a look at. The first one is called X64 Debug. This link is currently broken, but that one is commonly used. I'm going to get it fixed, I promise. All right, it's forever whack-a-mole. That X64 Debug is great if you're going to be doing like userland exploitation. Right, you're going to just exploit some binary that's on userland, which is what we're going to do for the most part of this. The other debugger that I argue is probably the right one to use is WinDebug, which is this guy right here. Now, the reason that I say WinDebug is the debugger that you should probably learn to use is this is the official Microsoft debugger. All right. WinDebug also has a very nice terminal interface, which you'll see me use like quasi here in a few moments. WinDebug is the only debugger that can do, as far as I'm aware, that can do kernel debugging. You can even debug yourself using WinDebug. You can debug your own kernel that you're running the debugger on with WinDebug. It does this like crazy snapshot thing. That's kind of cool. I'm not saying it is the ultimate tool, but I think it is the correct tool for you to start on, because there are many cases or problems where only WinDebug or WinDebug is the only tool that you can use. Right. So let's take a look at this this binary here. As you see, we're using our GUI. We're going to run that smoke test binary. And what we get here is a blinking terminal window. Why? Any guess? Well, it is running. It's running right here. So the program is a terminal program, right? So it needs to run in a terminal. But we didn't have a terminal when we started this, because WinDebug could be debugging a GUI application, could be running a terminal application. In this case, we're running a terminal application. We need to start a terminal that is running it. And so the terminal popped up, and we are at a familiar, right? We've seen this before, right? It's our friendly CC byte. Right, this address looks funky, you say.
It's the slash.
What's the, so it probably looks like a slash, and I don't know that I'll be able to make the, oh, I can. Make the text bigger. It's a backtick. So they do this to make the addresses easier to view. This convention exists across anything. You don't need to know what I'm doing here. But like this right here, I just dumped out a bunch of quad words at RSP. This is the memory location. This is the value. We see we're still incrementing by 16 bytes as far as memory location. So this is the first 8 bytes, the next 8 bytes. And you'll just notice all memory locations have this backtick in the middle. Does take a little bit of adjusting.
Yeah.
Okay. And so that's just how the tool represents things. Now, one of the things that I said I'd try and explain, we'll see if I got everything working correctly. Oh, I need to do something. was I said we had not X, Y. We had this PDB thing. When we debug and work on Linux binaries, we can say this binary is compiled with symbols. We can say this binary is compiled with debug symbols, or we could say this binary is compiled and it's stripped, so it just had none. Okay? In Windows, the debug information is actually in a separate file, right? And it's part of the reason why these aren't just named level 1, level 2, because the name of the files at compilation time matter. In Linux, your file extensions matter for the most part. No, right? I can name a text file myfile.mp3, and I can open it in Vim, and it's totally fine, right? The fact that it ends in .mp3 doesn't matter. On Windows, file suffixes matter a lot. File names matter a lot. And so there's actually a connection between this file having this name and this file having this name. And if I were to rename them, the debugger would not recognize that these are related.
What does that have to do with level 1?
This is, so if I were to rename this to level 1,
Rename that.
it wouldn't work. At compile time, inside this debug file, they use a unique identifier and a unique hash of the file and the file path. So changing the file name will break the relationship between the executable and the debug information. There are ways that you can run commands inside WinDBG to force import and ignore this information, but then you can get some other strange behaviors. Where all of a sudden symbol information may not even be accurate because the debugger decided to assign the wrong symbol to the wrong. Just that's why this is how it is. All right.
I'll buy it.
Okay. All right. So what I'm going to do, and I don't know, this is where we can find out together here. I'm going to copy from Y our PDB and bring that over here to C. So now on my C drive, hopefully these two are right next to each other, and the debugger says, "Hey, we're happy." Right? It may not. Now, what do I mean when I say this will be happy? So one of the commands that we typically run when we're on GDB, we're thinking about memory of this kind of running process of something. Windows is we run like VMMap, right? And we think about these shared libraries and the binary are like loaded into memory. There's going to be a lot of very similar concepts with Windows, but we're going to use very different terminology. In Windows, the terminology here is these are modules. All right. So our image, which is Baby Win Smoke Test, is a module that is loaded into this running process. Similarly, you will pretty much always see these three things, which is totally fine if you haven't seen the pre-recorded lecture videos. Very interesting thing that's different about Windows compared to Linux. These are all involved in how we get from a userland program to performing a syscall, which I go into a bit more detail in the pre-recorded lectures and step through it. You can see where these come to play. But you can think of these three things as the equivalent of like libc. Right? It's not libc, but it plays a similar role.
No.
Yeah, it's a loose analogy. Right? So I'm listing modules, and we can see the memory ranges where these are mapped. We also see, sad day, no symbols for that guy that I copied over.
Maybe if you close WinDebugging, open it again, because you just moved it.
Yeah. So there is a command to force reload. It's like .reload something, but let's see.
Still.
All right. Let me try the one over. This is why I said the path name, like it is super particular. See if I get the one that's at Y. Do I get my symbols there? No. Gosh dang it, Windows. Okay. let me think. Do I still have baby win test? Let's see. That is that. All right. Okay. But you'll notice that these are links. They look like links. The debugger is simultaneously a graphical debugger and a textual debugger. And so I can do things. So can I break it main? Do we know main? No, of course not. Get there. In GDB, we have step. WinDebug, it's T for trace. In GDB, we have C for continue. In WinDebug, we have G for go. Some of these are things that you're just going to have to.
Going to need to make a cheat sheet.
Yes, you'll make a cheat sheet. That's the point of this module, right? None of these binaries are complicated. They are all the equivalent of here's a buffer overflow, like jump to some shelter, right? Here is something that has ASLR, deal with, right? And they're very clear about like what does this do? And the reason is so in theory, you can spend time adjusting to this for this week. So that way next week or 2 weeks from now, it's been great. You'll have a bit more comfort for like, why am I hitting T? Right? Where TC is to trace until a call, which is actually a cool function. If you think about
Until the first call.
Yeah. It's continue until the immediate next call. But this is actually probably bad because there's something else that exists in Windows. So when we attach something to GDB on like a normal, sane, single-threaded process, how many threads are there?
Single thread.
It's a single-threaded process. This isn't a trick question, right? How many threads are in a single-threaded process on Linux?
Like 5.
All right, close. It's sometimes it's not 5. The single-threaded process on Linux has 1 thread, right? The way that debugging works on Linux is via a mechanism called ptrace, where the debugger causes the Linux process to kind of interrupt, right? And pause, and then we inspect it. The way that debugging works on Windows is you inject a debugging thread into the running process.
So it's a different thread from the main thread.
Yeah, so I'm not seeing it right here, which makes me a sad boy. Let's CP winbins L2. No, I want to be over here. Let's CP. You can't see it. Recurse for recursive from Z, which is going to be my home directory, winbins L2 here. And if I go into L2, this would be a better program to run debug because we can attach to it and we'll be in what we want. So this is your second challenge. It says, hey, there's a buffer overflow, and I tell you where win is. Right? Like I said, these are trivially easy. And that is by design. So let's see if I can run this here. And let's attach to that binary. All right. Squiggly. Why? The curse of the live demo, man. The tilde, that's not tilde. What is the squiggly called?
Tilde.
Is it tilde? All right.
At least that's what we call it.
I have to mash refresh, find this. Should show us. Okay, there we go. Things work now. Show us the threads. So this is saying list the number of list all of the threads that are in this process. Currently, there's 2 threads, and we also see this down here. All of the information that you can get up here, which is where I'm going to work, there is a graphical equivalent. I personally feel that given the Dojo environment, it's a lot easier to work here than it is to start popping up GUIs and things like that. Because like if I want to look at the disassembly, okay, well I can pop this and okay, now I see this, right? But then I need to pin this because I want to have my disassembly be here. Okay, now I have the, like you start, okay, maybe I want to see my registers too. Okay, and we pin that. Like this starts to become a mess pretty quick. I think on a real local setup, you can set this up in a way that makes a lot more sense. It's hard to do that in the Dojo interface, but it does exist. So right now I am on the wrong thread. And we can see down here in the GUI interface, the bold thread is remote breaking. This is the thread that GDB is injecting. I want to look at the thread that is actually running the process here. 2 ways I can do that. I can double click this one here to change into that thread, but I'm going to try and use text interface here. So I can say thread 0, and this would show me the information about the thread, but I haven't actually switched the thread. See, I'm still bolded down below. The correct syntax here is going to be %0s for setting the thread, right? We are going to say thread 0 set. And now, if we look, I'm inside NT read file. You don't have to know what NT read file is right now. You can trust that it's very similar to read on Linux. Okay? Now, I probably want to know where the heck in this program am I, right? So what would I want to do on Linux to read about this? What might I want to look at?
Backtrace.
I want to look at a backtrace. The answer is K. All right. K will give you the backtrace here. And so we can see the call stack. So I am inside several calls with this simple buffer overflow with some offset here. Eventually, this calls into kernel base. This is one of those module things I said, hey, this all results in kind of a libc translation into forming what we think of as a syscall. With this is going to call into kernel base, which then calls into ND DLL, which is where read file is. And that's where we currently are. Do I get symbols?
Is they're all baby possible offset function calls.
Yeah, that's why. That's why, because we don't have the debugger is very not happy about symbols. So there's 3 different things that you'll see here as far as the module. The intention for this module is for you to have symbols on all of them. You will either see deferred, which is what we saw when I first attached thing. That means that the debugger thinks that they're symbols, but we don't need them yet, so it's not fetching. When we use like the Linux debugger, we reference symbols locally. For the Microsoft symbols for like this kernel 32 NTDLL, these will actually get pulled down from a symbol server that Microsoft runs. And so when you first start up, it'll be deferred, and then it pulls them down and caches them locally, which is what we see here. This is the local cache because it's now pulled it down. But that's how that works. So it's a slightly different mechanism. Once WinDBG has the symbols, you'll see PDB symbols, and then you'll also see no symbols if it is just not happy. I'm going to try and see if I can force this. C, I need quotes. C, where am I? CD L2. Okay, it likes that. Then I need to reload. Do I have it? No. It's going to keep that. I want you to see it with symbols. Otherwise, this becomes much harder than it needs to be. Okay. Well, we're at the hour mark, so let's pause that, and I will force this to work.
Before you pause,
Yes.
are we gonna have an extension?
Oh yes, good call, good call. Get me on camera. So somebody asked before class if I could move the deadline for heap 2. They were asking for a day. Um, Honestly, the difference to me between like a day and spring break is one and the same. Because it doesn't matter to me. When is? I should look at my phone. I want to put calendar on stream. Spring break. How about I give you an extra week? Put it on the 11th. Is that fair? All right. So I will add a week to heap 2. It'll be due on the 11th. It's a bonus week because I still want you to solve this stuff once it works. But since it doesn't work, that is totally fair. All right. Anything else before I throw up the old thing and try and make the debugger happy? Nothing? All right. I'm going to hide in shame now. Boom. All right. We had an interesting conversation, which was really repetition of stuff that's in the pre-recorded lectures, if Twitch is interested. And what is going on here with NTDLL, kernel 32, kernel base? Why do these things exist? The answer is that Microsoft wants you to use these functions, like read file. This is the equivalent of like a Linux libc wrapper. And then how these kind of Win32 API functions work is they are going to translate what we provide in userland and map them to the actual syscall, where the syscall is this native API, which we see has a lot more arguments and is a bit more complex. And so in order for Microsoft to have a kernel that they can kind of evolve over time and change how the kernel works, they need to have two different libraries. So there's the Win32 library, which for the most part, Microsoft says they won't change, right? Read file will always be read file. It will take these arguments and Microsoft will figure out how to make it work. And then in Microsoft's implementation of read file, it will call this syscall NT read file, which clearly has quite a bit more going on inside. But as a normal userland developer, I do not need to think about this native API. All right, so while I was hiding behind the perpetual loading screen, I did a whole bunch of magic, and suddenly I have a binary that has private PDB symbols. The intention is for all challenges in this first module to provide you with symbols so that you don't have to step through all of this in blind assembly. So what does it mean to have private PDB symbols? It means that when I look at this, I can get a list of all functions that are inside this binary, right? Now, when we think about a Linux binary, we typically don't have that many symbols in like these small little things. This is like a pretty trivial binary that I have here. But there's actually quite a bit of symbols inside of a Windows binary. And now, if I want to reference or set a breakpoint at these things, I can, it's B, the one you almost always want if you want to set a breakpoint is BU. There's actually like 3 or 4 different kinds of breakpoints. BU is like 99% of the time what you want. It has to do with whether or not the symbol is resolved or unresolved. BU is the way. So now if I go back and hit K, why do I see this nonsense? I did cover this.
See a breakpoint.
Okay. I am at, we have RTL user thread start, which calls base thread init thong, which calls debug remote break-in, which then calls debug breakpoint. What's happening?
Backtrace. I thought you continued.
No, K is in fact a backtrace. And so I'm looking at a backtrace that says this. Where am I in my binary? Do I know?
Are we in our binary?
I am in fact in the running process of this binary.
So we stopped at the breakpoint.
Where am I? What happened?
In NTDLL, yeah.
So I'm in the wrong thread.
Oh.
Remember, the way that WinDebug works is it will default you to this debug thread. And so the way that it inserted this thread is it called this user thread started, injected this thread, it init this thread, and the thread immediately said, hey, we're going to cause a breakpoint. Right? And so we are in the debug thread and not in the actual running process thread. We could double click on the thread down here in the bottom right if I have a pointer. That will change us. And then again, squiggly 0s would do the same thing. Now if I hit K for backtrace, since we have symbols, this now looks considerably more legible instead of just having these random offsets into the module, right? We see the module's name followed by an exclamation point followed by the function. It turns out you can have functions that share the same name and you reference them as module name, exclamation point, function name. Now, right here, this is challenge. These challenges follow a convention you've seen of main calling challenge, challenge having something interesting going on, and you need to exploit the challenge function. So one of the things that I may want to do is look at the assembly of challenge. In GDB, we think of disassemble. The correct terminology in Windows is unassemble. So you want U, okay? I want to unassemble a function, and I want to unassemble this function right here, baby when simple overflow, no ASLR, exclamation point challenge. If I do that, we get the assembly of this. Again, we have those tildes, right? But this is still just assembly, right? We know how to read assembly. Now I'm inside the call to read. See if I can find that. There's a printf. So I'm in this call to fget. So let's set a breakpoint just past it. How do I set a breakpoint? BU. Okay, I can list the breakpoint BL. We see it right there. I'm going to continue with G. All right, we're going to go. Okay. Where is... Boop. Here it is. So now this is very much like when we had GDB before, or GDB before, but this is blocked waiting on some input on standard in. So let's give it something. And we see that we have returned, and we are now at our breakpoint. I'm even giving you source. I like this. I'm not giving you the literal C file, but inside of the debugger, you can get that.
Can you set the breakpoints in the debug?
Can I set the breakpoint in the debugger? Yes. So you can click over here in this column, right, on the source to set a breakpoint if you really like doing that. I don't believe you can set a breakpoint on the assembly there. You should be able to set a breakpoint. I'm a liar. You can't set a breakpoint on the disassembly screen.
You haven't said it yet.
What's that?
You haven't said it yet, so it's a lie.
Ah, well, that's good. I try not to lie. So now I'm just on the other side of this read. Now, one of the interesting things that we may want to do here, this challenge said what? What was the output of this challenge?
It gave us the other solution.
Says this challenge is vulnerable to a buffer overflow. ASLR is disabled. Use this to call the win function, and it tells us where win is located. Okay. What is something I may want to know at this particular juncture?
How big is our buffer?
How big is our buffer? So in this case, you have source. My buffer is 632. Okay. How else could I know that? Well, we could look at the assembly. I promise you, you will not have source for everything in the future, but we'll be nice today. Well, we see that there's a call to fgets. Anyone know what fgets does? What the arguments are to this thing? It looks a little weird, doesn't it? So if we try to apply our Linux knowledge here, how do function calls work on Linux?
Values get loaded into registers and all gets called.
Right, so things get loaded into registers and then you perform a call, which then calls a function. And that is pretty much how things work in Windows as well. Except we're going to use the same registers because the calling conventions that we've learned thus far are the system SysV64 ADI, But it's specifically the Linux 64-bit calling conventions of RDI, RSI, RDX, or CX, R8, R9, right? Windows uses a different calling convention. The calling convention is referred to as fast call. There's a few things that are interesting about fast call. The first is that we use different registers. If we were to scroll down here, it should tell us the answer is RCX, RDX, R8, R9. Is it hiding in here? Okay, I don't see it immediately in the docs. It is hiding there, but trust me, it is RCX, RDX, R8, R9 are the first four arguments. We do not use a register for a fifth argument. Ever.
We just use this type.
Right. Well, what did we do in other in Linux when we had something that had a bajillion arguments like printout? Arguments ended up on the stack, right? For a long time, arguments, if you were to look historically at like 32-bit implementations of Intel CPUs, arguments lived on the stack. It's kind of a more recent thing that arguments live in registers. And so there's only four registers that are used for function arguments, and then things end up on the stack. I said it was RCX, RDX, R8, R9. If we look at this fgets call, does this start to make a little bit more sense? Well, we're setting something to RCX, we're setting something to EDX, we're setting something to R8. It looks like we didn't have another argument there. Fgets does in fact take 3 arguments. So that makes sense. Character pointer, a size, and then a stream. So what I have here, a character pointer, which is RSP plus 30. So what is RSP plus hex 30? Yeah, if it's it is being loaded into RCX, so it is what argument?
Third. First.
First.
Yeah.
The first argument is RCX. It's RCX, RDX, R8, R9. I'm looking at the Linux man page. I'm sure I could find the equivalent on Windows. The trick here for the equivalent of a man page, but with Windows, is you type MSDN and then the thing that you want, and then you let Google do its work. Look, it works the same. We have character stream number, or a pointer to a buffer, number of characters, and then where we're reading it from. Yes.
Isn't this C fgets?
Yeah.
So why is it different between Linux?
It's
still the C.
It's not.
Yeah. Well, why would we expect it to be different?
Why
not just?
We wouldn't. I'm just showing how to.
Oh,
Right, it seems a little silly for me to be like, here's fgets in Windows. Let me show the main page for Linux.
Yeah.
Right? You're correct. So the observation was, isn't fgets part of the C runtime? Right? This is a C level. This is a language level function, and that's correct. Right? So why would it be different? We're writing the same language. Right? C is C, and that's true. But what would be different? What would be different between calling fgets in Linux versus calling fgets in
Underlying syscall implementation?
Yes, the underlying syscall implementation, right? So we could envision, I don't think we need to write it out, but if I were to write something that calls fgets here and compile it on Linux around strace, we're probably going to see some read calls, right? Maybe it called scanf, maybe, probably not, probably called read. Right? We are strace it, we'd see that read is the underlying syscall that is being called. But what did we see over here when we looked at our backtrace? What was getting called? You got to keep going up a little bit. Did I skip it? Boop. Boom. We see, it's actually the line above it. We see that the native API, there is no read being called like Linux. Instead, the equivalent is nt read file, right? In both cases, I'm calling fgets, which is going to be somewhere in this stack right here, common fgets. Everything in the implementation of fgets is what's going to be different. So this is the first argument. The first argument is a buffer. So this is being placed where? Can I? You want to see your registers? R for registers. That one does make sense. I'm on board with that one.
That's the only.
It Microsoft and Windows has been around for a long time. There's a lot of things that are around for legacy reasons. The WinDBG debugger actually has 3 completely different syntaxes that can be used, like 2 completely different languages that can be written right here. I'm showing you one of them. There's an object-oriented one, there's an evaluative one, there's this, and then there's 2 different like macro syntaxes as well. It's like an insanely large and powerful thing. But as it's evolved, there's certainly been some growing pains, right? Like especially if you come from the Linux side. I don't think it's ridiculous though. So if I want to just print RSP, I can RSP. So what I'm interested in here is RCX. Oh, RCX got messed up. Gosh dang it. Because I want to try and find the distance for this buffer overflow, right? I happen to have symbols here, right? So I can use buffer. So we'll have to just kind of cheat there. I could have found it in RCX, but at this point, RCX is conglomerates from fgets. So this is where a buffer begins. This is my random ASCII characters that I happen to type here. And this is going to follow that same convention of I start typing, I go this way, right? Numbers are still numbers like you see in GDP. Now, I keep doing just like DQ. This is for dump quad word. There is, for instance, I think DF, if I want to, DF would give me dump this as floats. Right? I don't know why you'd want to do that, but you could. We can dump doubles. In this case, I like DQ because we are used to seeing quad words from GDB. But where do I want to overflow to? If this is where I start, how do I know how far I want to go?
You know how large the buffer is, so check that much offset from the start of the buffer.
Okay, so your working theory is we stole from the source here. It's 632 bytes. Excuse me. So 632 bytes from this. Maybe that's where the end is.
Well,
No, but like it's a fine place to start, right? I'm not knocking it. I am incapable of doing math. Anyone know what 632 roughly divided by 8 is? Ooh. 79. All right. So I really want to look at like, I don't know, say 90 quadrants, right? That's what I want to see. You can specify that. This is just the default length that it's showing. I want 90 quad words. The mnemonic there was dump quad words starting at buffer. I want a length of 90. So we have this L90 syntax. Okay, so here is all of that space. But I probably want the equivalent of info frame. I want to know what is this return address, right? Where is this? One of the nice things that this debugger will let you do is if you double click on something, did I not go far enough? I didn't go far enough. Okay. You need more than 90. If you double click on an address and it exists somewhere else, it will highlight.
Does highlight rather.
Did you see it?
Well, if you go up, it highlights that. Like the return address.
Yeah, okay, yeah. So we see it highlighted in itself, but we don't see this return address on the stack. That makes me very sad, because I am expecting to see this on the stack. Function, fine.
This is because we're inside of like F gets called a bunch of
Oh.
stack is not the stack, but
Well, but I'm looking at we're not inside fgets.
no.
No, we continued to this point right here.
Oh.
Right? And so if I were to unassemble challenge, we are right here after this call to fgets. Right? And so we should see it. Oh, wait, that's a big number. It's a big distance from RSP, isn't it?
Why such a big distance?
That is a good question. I'm going to guess that our source is lying to us. Assembly is the one true. Assembly, it doesn't lie. Fancy debugger stuff, all lies. And it makes a bit more sense here, because how big is this? It's subtracting RSP by 2B8. Oh, do I have hex? I don't have hex. Give me IPython. 2B, what did I say? 2B8. Divide that by 8. 80. No, that came out right. 87. Why don't I see that? I should be able to dump quad words. Let's try it at RSP. Let's assume buffer is cursed. 90 long. And then I'm interested in the call stack. I want to find this value. Oh.
That's there.
Oh, it's L90. L90. Get this. I double tap him. There it is. Okay, so the symbols ruined us, right? But when we look at the assembly, we find the truth. It makes me feel good. Okay, so we see this is where the saved return address is, and if we were to scroll up, why I had to dump from RSP instead of buffer, I don't know. This is where our input started. So now I have two addresses. I can subtract them. Begin with a question mark to enter evaluation mode. Right, there's a lot of interesting things you can do there. I'm just going to use it to do subtraction. And so what I did was I double-clicked on the return address from the current function frame, which we see right here. It's going to be this address plus 8. Change it to an 8. Find the distance. 648 is my distance. Okay, I think I have enough information to solve this. You guys agree?
No.
You
How
don't.
do we send the payload to the child?
How do I send the payload? So this is an interesting gamble that I'm willing to take this semester. So we couldn't do this last semester, but I was recently informed, and I know there's been several efforts to do this, but I tried. I messed around with this while I was working on the Windows stuff. Pwn Tools Dev, it's not in main, has decent Windows support. It's the whole reason that we aren't doing this weird netcat to some weird port, and then I just hand wave and say, yeah, this goes into Windows. In the past, Oh no. What students had to do is they would write a Pwn Tools script inside the Linux environment, and they would have to use Pwn Tools remote and connect to localhost on a specific port that would then connect to the VM. That worked. But it had a number of problems because all of a sudden everything is a network interface, right? And so that meant when we wanted to do things like flush bytes or deal with I/O, you could get weird buffering issues since we're now suddenly everything is over the network. Right? And so for this semester, the intention is everything will be solvable entirely within this Windows environment. You're welcome to use the Linux environment, but you should be able to solve stuff locally here. So I can run PowerShell here. This is the same PowerShell that I have over here, right? But I could do the same stuff in the GUI if that's my can of worms. I'm going to make the classic do.py. All right. Now, since, as far as I'm aware, Windows does not have a shebang.
Oh,
Right? So instead, we just write good old Python code. From pwn import star, p equals process. In this case, this thing is called what do I want to do? We said this is a buffer overflow. There's 648 bytes to the saved return address. And then there's some I/O that the challenge does where it tells me where when is. Not a trick question.
Send the payload.
So send the payload. What is the payload?
648, like random garbage bytes and then return address.
Okay, I'm sending 648 garbage bytes plus.
Return address. Like the return address is so big.
Yeah, but how do I get this return address?
It's given in the chat. Then.
Okay, you want this?
Wait, does it change every time you run?
is it PIE?
Yeah.
So it's a good question. It says ASLR is disabled. If I were on Linux and I built something that was PIE and ASLR was disabled, would this change?
In Linux?
Yeah. So the same logic applies here. So this should be a constant address, and as you get to like the third to fifth challenge, we start introducing ASLR. You will have an opinion about ASLR.
That I don't have already.
Yes, you will have a brand new opinion about ASLR.
I think I've heard about this one. Well, I don't know if this is true, but
You want to spoil the fun?
can I?
You can. I say it in the pre-recorded.
I think ASLR only runs once, so it doesn't really work like we understand. Like if you run the same binary multiple times, ASLR doesn't change the stack space doesn't change. It's the same every time you run the binary. It's just once the kernel gets ran, I think.
So I'm going to phrase it a little bit differently, but you're there. So the guarantee that Windows username ASLR provides is that the address is only guaranteed to be randomized per boot.
Oh,
okay. The statement from the class was that it will always be a fixed address. Like even if I had said ASLR was enabled and had this compiled with the equivalent of PIE, that this would always be the same. That's not entirely true. You can get, and I want to say in the pre-recorded lecture videos, I demonstrate this, if not definitely in the live class that I did from last year that are included in this module. I show the ASLR. So Windows, for historical reasons, Windows modules had something that was called like a preferred base address. And so this is the location that the library wants to be loaded into virtual memory, right? The problem is that like if you have multiple modules, they may want to get all loaded into the same spot. And so then you'd have a conflict. The preferred base address concept exists on Windows as a performance optimization, because then I don't have to remap all of these things to different places, right? It's just the map is consistent every time that you run. But the preferred base address is kind of a suggestion. And so there are cases where modules will have conflicting or overlapping preferred locations to load into memory, at which point the OS will load it into a different spot. The effect of that is if you run something that has ASLR, that's just throwing out its address, the first 1 or 2 times it might change, but if you run it like 5 or 6 times, it'll end up being a fixed address.
This is when ASLR is enabled.
This is when ASLR is enabled. Right now, there's no ASLR, and so this is just a constant.
What if the modules overlap when there's no ASLR?
You can't do that.
Doesn't happen.
Well, so there's ASLR is randomizing. There's a difference between ASLR and the preferred loading address, like the base address to load a library, right? ASLR will randomize part of the address that gets loaded in. The dynamic base address is a performance optimization for those functions so that Windows doesn't have to rewrite how they get called, right? Like in Linux, every time we start up a function, if Jan has a lecture video called like the life cycle of a Linux process or something, it's hiding somewhere on the dojo. It's actually a great discussion, but it doesn't like map one-to-one to a module. And so I don't know that as many people see it as probably should. But in Linux, when a process starts up, the loader has to fix up a whole bunch of stuff, right? We have the PLT, we have this like dynamic linking, we have to overwrite and change stuff and make the binary behave sanely in this random address space, right? Windows, and that's like a security trade-off that we make. Windows will strive to err on the side of performance here. Like it's a trade-off that they're making, right? They say that, hey, you just don't leak this, and then it's good, and nobody knows it. A side effect of this, which I think would be a cool challenge, is it's my understanding that you could leak an address of a module in one binary, run another binary that loads that module, and you have a high likelihood of the memory location that being loaded in being consistent across. Again, performance optimization, because now we can just, and it's the same everywhere.
This defeats the purpose of ASLR.
It depends on what your security model is, right? So this ASLR behavior is something it's very easy for us to like, what's going on here, especially after you spend a lot of time in the Linux world, right? One of the things that these challenges don't hit that I'm probably going to add in some free time that I'm going to have later this week, since we're going into spring break. I do talk about it in the pre-recorded lecture videos, though, is the stack canary. Stack canaries exist, right? I'm not throwing them at you in these challenges because the point is to just get you messing around with the debugger and thinking about what's going, right? It should be easy, but spend time practicing the commands. Just start thinking GD continue, right? That's why this is a light one, because it's learning new tooling, learning a new workflow, working out kinks there. But the way Windows stack canaries work is actually different than the way Linux stack canaries. So on Linux, we make this assumption that the stack canary for one function is the same constant value for the next function, right?
In the same way.
Yeah, within one running process, the stack canary is a randomized value that is determined at process launch. You agree? Or at exec. Yeah. And so if we have all of these function frames, that's the same value that is protecting every return address, right? And that seems totally reasonable to us on the Linux side. If you were a Windows person, you would laugh at that. There's Windows stack canary. Their terminology for it is stack cookie. No, stack cookie. The stack cookie is actually more complicated than what we do on the Linux side, because they would think it's silly that we use a constant value.
Why is that?
It's an implementation detail.
I use a constant base.
But I mean, it's an implementation deal, and it depends on what your security model is, right? This goes back to something that you probably heard someone rant about in your undergrad, right? Security is all a matter of like, what is your threat model, right? What do you consider acceptable and not acceptable? How much does performance matter? Why do we teach libc 2.31 for the Tcache, and then we have challenges that use libc 2.35? Why? Because the trade-off between those libc versions was different. How important was performance versus security, right? All of a sudden we have stapling. It seems silly that we have this XOR, and you're like, it's just a single XOR, right? That is cycles of a computer, right? And there are performance implications for having that on me. Windows does something similar to safe linking with their stack code, where there's value that is different for every stack frame that gets XOR'd with a constant that then gets written to the cookie or gets written to the stack canary. So that means that every function frame, the stack canary is a slightly different value.
In an unpredictable. It's like
I am not going to say whether it's predictable or unpredictable, because I'm probably going to write some challenges around this. It's been on my to-do list. But the point is that just because this seems like, why would you do this on Windows, right? ASLR having that side effect. It's because in their model, you shouldn't have a program, their security model, like what is reasonable behavior. You shouldn't have a program that is going to be yeeting out, arbitrary pointers. That shouldn't happen. If that doesn't happen, then all you do need to randomize is once per week. So why deal with the performance overhead of randomizing it every time you start a process? Because you shouldn't be doing that in the first place. They're not saying it's right or wrong. It's a different way of thinking about it. Where the stack canary, they care a lot more about that than we do on the Linux side. And you'll find that there are minor differences in many of these areas that we've seen. And hopefully that's what we'll take away from this initial poking at this stuff. Because the second half doesn't map nearly as well. It's very Windows specific, which will be interesting to see. Okay, so we have this constant value. I double-clicked it over here, got it in my clipboard. I'm grabbing it from this clipboard and bringing it over here. I can still just P64 this bad boy. P interactive. Any believers? You're not given how the first half of this class is going. I don't play.
No, I think there's something with Windows. That's why. I'm not doubting you.
No. You're welcome to doubt both. Okay. The one thing I hope people
do the Y from the C, but from the Y.
So this
Was already there.
And this is, I have already made that mistake many a times. This is Tmux in Linux, where some of my terminals are in Windows and some of them aren't. And so I am doing a reasonably good job of mentally keeping tabs on that. Like, I'm pretty sure this one is outside. I'm a liar. But this is outside, right? This is in the Linux environment. And you'll also notice, I don't think Vim, So I didn't install Vim in Windows, but I did install NeoVim, because that is the correct Vim, if you're a Vim user, which you can get over here on the nvim command. If there is something that you just really, really want on the Windows side, let me know. I'll try and add it. Just know that it's going to take like literally a day for it to, assuming I type stuff correctly, it'll literally be a day for me to get it onto prod. Yeah. So, okay. So we are in fact in C baby win. That is where my do.py is. My do.py is not particularly crazy. We run do.py. What happened?
Should be.
You sent the bytes before
Oh.
it read it. Yeah, so you need like a wait maybe out of the process.
No.
Or
So the statement was, oh, I sent the bytes before it called fgets. All right, we still have streams. Like could I do that on the Linux side? I write the standard in before it calls read. Yeah, it just chills in standard in until the program tries to read from it. This is not something like super crazy Windows. This goes back to the thing that I have to try and sneak into every single lecture. Reading the man pages. So fgets will read until what?
Null.
Stops reading an EOF, which we haven't sent, or a new line.
Send lines.
I haven't sent the new line. It was a deliberate troll. We hit enter. But we do get the Windows failure. That's because in order to make the debug symbols work, I freshly compiled this and I didn't re-sign it, right? This is all nonsense that you don't need to know about, but you can see more of my behind the scenes spring break bonanza that I'm going to be having. Sign tool, sign F. This 256 of what is this thing? This thing. Oh, it won't sign it because our debugger is got a handle on it. So in Linux, we primarily deal with handles, like the concept of a handle is like a file descriptor when we open a file. But this kind of pattern exists for all sorts of resources, and it is used extensively by the Win32 API. So you can have, for instance, a handle to a process, which is, we'll see in 2 weeks, that with a handle to a process, you can inject threads into things, which is how the debugger works and why we have this weird like dual thread thing when we attach a debugger. Turns out you can just do that. You can just be like, oh, that process over there. You now have a thread, and it's me. Okay, so now it's signed. Let's run our do.py. We mash enter, and we do, in fact, see the flag. Okay.
So all we have to do is just descript. We don't need to worry about the flag working.
My initial rant about flag service and all of that was for my own edification more than anything. But I think it's important that you understand how the whole thing works, because otherwise, when you take a look at unassembling the function of challenge here, or no, it wouldn't be challenge. In this case, it'd be win. And you start being like, okay, well, what is this thing doing? Well, it has get flag. So let's unassemble get flag. All right. Oh, thank you for that. It doesn't know where this ends. And when you see here, you see, and this is an interesting thing that I rant about a bit, but you see create file A. A fun thing about Windows that we will inevitably deal with. What is the default encoding on Linux?
UTF-8.
ASCII, right? When we believe in nice, simple 8-byte characters. Windows has, remember good old widechar from file structs with Unicode? Windows, and you see this type of mnemonic here, where I called create file in my source code. I'm pretty sure I showed that. And that is the equivalent of open on Linux. But if I do msdn create file, you'll see that there is multiple versions of create file. There's going to be create file, there's create file A, and then I believe the other one's create file W?
Yeah, it's right
Is it?
there.
Yes. And this is because over time, at one point in time, Microsoft did want to go forward 2-byte characters as the standard. And so there are versions of functions that will be wide character. And then there are versions of functions that are going to want your single byte character, which is where I create file A for ASCII and then W for wide. This will inevitably trip somebody up at some point. I don't believe in the current stuff. So this is something that when writing the challenges I have to actively deal with, because there are some functions that want wide characters and there are some functions that want ASCII characters. And so within the challenge code, I'm converting between them in order to pass either long strings or ASCII strings to the correct function. Right? And so when we see create file A here, we know that this is a create file where the argument is going to be an ASCII string and not a wide character. But this very easily could have been create file W, in which case the argument is now a wide character string, which has all sorts of interesting problems for you because you're going to have a bunch of null bytes, right?
Because it's bigger. Because it's just 2 bytes. So instead of just one.
Right. And so what happens if your input now is not null byte friendly, or null bytes have other ramifications, right?
I love that.
It can become its own problem. But I explained the flag service so that way when you look at like this get flag and you see create file A that's taking an argument, we'd say, okay, well, what is the first argument to create file? We trust our handy documentation here. I mentioned this in the pre-recorded stuff. It's a Windows convention for their types. They like to macro this. Anyone want to take a guess on what LPC STR is?
Tell you what STR is. String.
Okay. STR string. All right, I'll buy that. Anyone want to take, I'll even go one further. C string. Right? A C string is as we know, is an array of characters that is terminated by a null byte. Right? That is what a C string is. So then what is LP? LP is long pointer. Okay, so it is a pointer that is a keyword that points to a literal C string. And this initially looks like, is this kind of like, what is this? But once you spend a little bit of time with it, it's not that spooky. Most things are long pointers to something. A D word, Q word, we've seen those before. C string would just be a literal, not that bad. Our first argument here is the file name. And so then if we were to go over here to our debugger, we see that we're moving whatever is at this. We'd have to break here and find it, but you'd see that weird pipe syntax for what's being opened, right? And if I didn't bring up how this whole thing works, that just becomes this like insanity value, right? Why are there like 12 slashes, the word pipe local, right? I don't want that to be something that you guys get hung up on. What this get flag is doing, as I showed in the source, is create file, which is the equivalent of open. It's then doing a read, and then it's returning that buffer to the callee, which then it just writes out. Right? It's literally open read write is what this is doing. It's just doing it over a pipe that communicates with the flag service. So based upon the the way the first half of this went, everything is broken and you should not start anything, which is the best. I'm going to try and fix that tonight. You can certainly watch the pre-recorded lecture videos, and I will try and make Windows not explode.
So why didn't you put the persistence module before Windows?
So the question is, why did I not do the botnets and persistent stuff before this? The answer is the botnets and persistent stuff uses the same. So like when we look at what 365 is doing right now, I can joke and say, hey, they're fork bombing and using a whole bunch of resources. The actual point of contention, as far as I can tell, looking at the production instance, actually has to do with the network translation layer of how that virtual networking works. They're just hammering that in the process of fork bombing. Like the slowdown isn't, we aren't like maxing out on CPU. We aren't running out of RAM. It's not a hardware resource. The resource that is causing issues is actually kernel contention, as far as I can tell. And so, you know what? If the problem with slowdowns on the dojo is doing all of this virtual network translation with 365, you know what would really not make it better? Giving you guys an assignment that relied on a ridiculous amount of virtual hosts and network translations.
With this 5 people, like what's the max we can?
Well, it's not that we were gonna do loads, that there's loads for us.
Yes. Yeah. It is.
Like
it
you
is.
can't make it any worse, is what I'm saying. From what already is.
We wouldn't be able to do the chat.
Yeah.
Saying it would be worse for us.
Yes. Yeah, it would be significantly worse for you because you are trying to pass something through multiple hosts. They have like 3 hosts. It's the same underlying, I don't know if we have that thing open sourced or not, but it's the same underlying library that is used to stand up the virtual networks for the botnet stuff. And so if that component is what's causing the slowdown, the answer is not, let's give you guys stuff that is going to hammer that exact same resource that we're constraining. So that was one thing, and the other thing is just that's not where I put in my time, right? I made the decision a little bit ago to switch to this direction, and then ended up spending more time addressing unintended solves that one could lever, not from these challenges, but from the infrastructure itself. There are some very savvy people on our Discord who every time I push a change would like DM me and say, hey, did you know? And then I would get sad. Which is part of the reason that we had changed from the networking side. Aside from the fact I think it makes more sense to just do Windows stuff in Windows, right? Use Windows tooling, try and stay in this Windows ecosystem if we're going to talk about Windows. There were some fundamental problems with how this VM stands up in the network proxy that were problematic in a way that was not trivially solved, where you could just unintended solve everything. And so to me, the solution was, well, I don't need this network proxy anymore. Like, let's just remove the problematic component from the infrastructure. It's a fair question. You'll find the back half of this course spicy.
But we are doing about this.
Yes, yeah, that is happening. It does exist. It doesn't exist in a state where I can be like, flip a switch and here it is, but it exists close enough where no, it is happening.
So if you push a change tonight, we will get to see it tomorrow, like after 8 hours. Right?
It will happen.
I will let you know when the production instance is behaving how I expect it to behave.
One afternoon.
It is at the top of my priority list because I did not come here today expecting to be like, hey, nothing works live on Twitch, right? That certainly wasn't my intention.
At least this one.
Well, I was able to effectively demo, right? But the reason I was able to effectively demo some of the things that I wanted is because I did demos, right? And so I have an idea of where these pain points are. Where for you guys, it would I'm communicating with the flight service and it says invalid process. What am I doing wrong? I'm telling you right now, that is not, that is not your fault. That's my fault. Or I'm debugging this and I don't have symbol. I want you to have symbol, right? Like these are things that should get straightened out, and that's on. And that's just where, like, I want you to know that that's on. All right. Anything else before I end the stream? All right. Everything's on fire as per normal.